Today, we're going on the hunt for an invisible force. It's a power that connects the little crackle you hear when you take off a sweater all the way to the raw energy of a lightning strike. We are going to demystify one of the most fundamental ideas in all of science, electric charge.
You know what I'm talking about, right? That tiny, surprising zap you get from a doorknob, or that crackling sound your sweater makes in a dark room. Well, it turns out those aren't just little quirks of daily life. They're actually our first clues to a fundamental force of nature. So let's start right there with these everyday shocks, because it turns out they are not random sparks at all. Nope, they're actually our most common run-in with what scientists call static electricity.
And here's the really fascinating part. All of these things, the little spark from your sweater, the shock from a car door, your hair standing on end, and even a massive bolt of lightning, they're all caused by the exact same thing. It's just a super fast discharge of built-up electric charge.
So that begs the question, right? What is this invisible charge really? And how in the world does it build up on perfectly normal everyday objects? Well, to find the answer, we've got to go way back in time. Our first big clue in this mystery takes us all the way back to ancient Greece. It all started with a really simple observation that, believe it or not, set the stage for everything we now know about electricity. So the story starts around 600 BC. A guy named Thales of Miletus noticed that if you rubbed a piece of amber, it could suddenly pick up light stuff like straw or feathers. For centuries, this was just a neat party trick. But then in the 1700s, scientists started experimenting and realized, hey, wait a minute, there isn't just one type of this effect. There are two. And then good old Benjamin Franklin stepped in and gave them the names we still use today, positive and negative.
And they figured this out with some really simple experiments. If you took two glass rods and rubbed them with silk, they would actually push each other away. Same thing with two plastic rods rubbed with fur, they'd repel. But if you brought one of those glass rods near one of the plastic rods, they'd pull toward each other. A clear pattern was starting to emerge.
And this property, this kind of two-sided nature that makes charges either attract or repel each other, has a name. It's called polarity. And it's the fundamental difference between what's happening on that glass rod versus what's happening on the plastic one.
So, boom, here it is, the first fundamental rule of our mystery, the one you probably remember from science class. Like charges repel and opposite charges attract. This simple, powerful principle is the absolute bedrock of electrostatics. It explains everything we've seen so far.
Okay, so we've got positive and negative charges. They attract or repel. Simple enough. But why do some things, like a plastic comb, seem to hold a charge so easily, while others, like a metal spoon, just don't? Well, it all comes down to something I like to call the Great Escape. You see, materials basically fall into two camps. On one side, you have conductors. Think of metals, or even our own bodies. In these materials, electrons can kind of roam around freely, which means charge can flow through them super easily. On the other side, you have insulators. Things like plastic, glass, or wood. They hold onto their electrons really tightly, so if you put a charge on them, it pretty much stays put.
And that brings us right back to our practical question. Now that we know about conductors and insulators, we can finally figure out why rubbing a metal spoon is totally different from rubbing a plastic comb.
Let's break it down. When you rub that spoon, charge does actually try to build up. But here's the catch. The spoon is a conductor, and guess what? So are you. That charge has an instant escape route. It flows right through the metal, through your body, and into the earth, which basically acts like a giant sponge that soaks it all up. But with an insulator, like that plastic comb, the charge gets stuck. It has nowhere to go.
Okay, we're getting somewhere. We've got the players, positive and negative charges, and we've got the playing field, conductors and insulators. Now, to really complete the picture, we need to understand the three fundamental, absolutely unbreakable rules that every single electric charge in the universe has to obey.
All right, the first rule is awesome because it's just so simple. It's called additivity. It means you can just add charges together like regular numbers. If you have a system with a +2 charge, a -5 charge, and a +4 charge, what's the total? You just add them up. 2 minus 5 plus 4 equals +1. That's it. Simple.
Rule number 2 is conservation of charge. And this one is huge. It means you can't just create charge out of thin air, and you can't destroy it either. When you rub that plastic rod with fur, you're not making new charge. You're just moving some electrons from the fur to the rod. The total amount of charge in that whole fur and rod system stays exactly the same.
It just gets rearranged. And the third rule, well, this one's a little bit mind-bending. It's called quantization. What it means is that charge isn't some smooth, continuous fluid. It actually comes in tiny individual packets. Think of it like money. You can have 1 cent, or 2 cents, or 3 cents, but you can't have half a cent. Charge is the same way. Every bit of free charge in the universe is just a whole number of these little packets. We call that basic unit E.
And just how small is this fundamental packet of charge? Oh, it is almost unimaginably tiny. The basic unit of charge, E, is about 1.6 times 10 to the power of negative 19 coulombs. I mean, to put that into perspective, you would need something like 6 quintillion of these little charges just to add up to a single coulomb. It's ridiculously small.
All right, we've cracked a lot of the code. We know about the 2 types of charge, we know how they behave in different materials, and we know the 3 unbreakable rules they live by. But that leaves one last crucial piece of the puzzle. Can we actually measure the force between them?
And the answer is yes, we can. Thanks to this man right here, Charles Augustin de Coulomb. Back in 1785, he built a device so sensitive it could measure the tiny, tiny forces between charged objects. He's the guy who took all these observations and turned them into a precise mathematical law.
And this is what he found. It's called Coulomb's law, and it's actually a pretty elegant rule. Basically, it says 2 things. First, the bigger the charges, the stronger the push or pull between them. Makes sense. Second, the force gets weaker as the charges get farther apart, but, and this is the key part, it gets weaker really fast. For the first time, we couldn't just see this invisible force at work, we could actually calculate.
So, just how strong is this force? Let's compare it to gravity, just between a single proton and a single electron. The electric force isn't just a little bit stronger. It's not 1,000,000 times stronger. It is, well, just look at that number. That's a 1 with 39 zeros after it. The electric force is about 10 to the power of 39 times stronger than gravity. That's a force so dominant, it's almost impossible to even wrap your head around.
And that leaves us with one final, profound question to chew on. If this electric force is so unbelievably powerful, so much stronger than gravity, then why does gravity seem to rule the universe? Why don't all the immense electric forces inside of every object, including you and me, why don't they just tear everything apart? Well, the answer lies in the almost perfect balance of this invisible force, but that's a story for another time.